Hi, everybody. Hi, Casey and Janelle. Welcome back to the live stream. And I'm not sure who else is there, but hi and thank you for joining. We are going to get right into questions 4 to 6. Put you here for now. Okay, so let me go to share. Hope you guys had a good day. Did you get to revise anything today? Or which topics did you look at today if you got to look at any? All right, Janelle, no problem. Get your papers and come. All right, so Casey said she didn't get to circuits, but it was hard. Oh dear. All right. This past paper doesn't have much in terms of circuits per se, but it does have a question where you had to work out the resistance and another one. What did we work out in the other one again? And then I had to work out resistance and something else. I'm trying to get to the question so I can tell you. Struggling with electricity and magnetism. All right, so maybe we can target that one for tomorrow. Like I do some past papers on that. So you can see how the concept is applied. What do you think? Tell me what you think about doing, instead of just choosing a paper tomorrow, we do it based on 9 questions that are electricity and magnetism. Yes, all right, that's good. So I will target that for tomorrow. We're going to look at mainly electricity and magnetism. All right, so in preparation for today, go and get an a diagram of electromagnetic spectrum. We're going to need that for today in that question. So make sure you have the spectrum and we can use that as a guide. So we're going to question 4. We need the spectrum for question 4. And then we go, the question 4 has to do with waves. And then we go into questions 5 and 6. I'm going to share now. So let me know when you start seeing. See my screen? Okay, good. So Casey says she's C. So let's now get into this question. Name the electromagnetic waves in each of the regions labeled A, B, and C in the electromagnetic spectrum shown in figure 5. So I'm going to mute my mic a little bit, but giving you an opportunity to tell me A, B, and C. What waves are those? All right, so I'm seeing an answer for A already. Is that correct? What's B? What's C? So I'm seeing B, visible light. Look carefully. Visible light is already labeled. If you look here, this section is visible light. All right, so I see gamma for C. Yes, saw gamma for C twice. But B now is the one that we need to make a little check for. Oh, yes, UV is B. Excellent. So we got A. Where is it? A is microwaves. B is UV. And C is gamma. Good job to you both. You did well. So let me write that in now. So this is microwave. And this is UV. And this one is gamma. Alrighty. Then we come to this question, which figure 6 represents some wavefronts approaching a barrier with a narrow gap, which is smaller than the wavelength of the wave. Now this part is important. The smaller than the wavelength of the wave, that is important. On figure 6, draw 3 wavefronts after they have passed through the narrow gap. What does the wavefronts look like after passing through a gap that is narrower than the wavelength or smaller than the wavelength? Kay says asking, if there is an acronym to remember this. Let me see. I'm trying to remember. I'm just going to do a search to see if I can find. I can't remember the one I used to use. That means not helping me. But there are acronyms. I mean, you can even create your own acronyms to help you to remember. I see one here where it says raw meat is very unsanitary except giraffe. There's that one. So that would be radio, microwave, I for infrared, V for visible light, U for ultraviolet, except the X is for X-rays, and the giraffe, the G is for gamma rays. So that's one. Let me see if I can find another one. And that's in the order of increasing frequency. Let me see if I can find. Here's another one. Raging Martians invaded Venus using X-ray guns. That one sounds like you can remember. I think I like the Raging Martians one. Rich men in Vegas use expensive gadgets. Yeah, that one is good too, Janelle. So Janelle gave us one. So rich men in Vegas use expensive gadgets. So really and truly, you can find different acronyms that will help you to remember the order. But you need to remember the order that you're remembering, if it's in the order of decreasing frequency or increasing frequency or wavelength. You have to remember that. So that would be in the order of decreasing wavelength or increasing frequency. So rich men in Vegas use expensive gadgets. That's a nice one. I like that one. So let's go back to the question. And the question I'm asking, if the wavefront is passing through a gap that is smaller than the wavelength of the wave, what would be the result? How would the wave look? I'm giving you 5, 4, 3, 2, 1. Okay, so let me give you the answer. Once the gap is smaller than the wavelength, then what will happen is the waves, after passing through the gap, will come out circular. So they will come out looking circular. Now, if the wider the gap gets, the more it starts looking less circular and more like straight lines. But once it's smaller than the wavelength, then you end up getting circular wavefronts after passing through the gap. Good? And that would be your 2 marks. Why? Okay. The most practical way I describe it is, if you have a hole, in something. Let me just draw a gap. And you have this thing to pass through it. And you're pushing it like that. When you push it through the hole, the smaller the hole is. Just think of it or picture it with me. The smaller the hole is, as you push it through, the thing is going to come through looking like that. True? Now, if the opening gets a little wider and you're trying to push this thing through it, it's going to be less curved. And then as it gets wider, so you might find it start looking like this now, because majority of it comes through just close to the ends that would be deflected or bent. And then now, naturally, if the gap is so wide that it can pass through, it's going to go through and come back out straight. So that's the reason behind why, if the gap is smaller than the wavelength, it's going to end up being circular. And she said, okay, Mister, that means she got the idea. All right, good. Okay, so now we go to the next question, C. So we did A and B already. Define the term refractive index of glass. Now again, I'm going to say to you, the mere fact that they placed of glass in the question simply means they want you to define it, the refractive index with relation to glass. It's not just good enough to define refractive index. You have to define the refractive index of glass. All right? Now, refractive index, as we may know, or I'm going to remind you now, is the ratio that tells the speed, how the speed of the wave will be affected as it goes from one medium to another. All right? So, the refractive index of glass, it is a ratio that tells how much the speed of light will be changed as it goes from air rather, into glass. So that's what the ratio is telling you. It's telling you how much the speed of light will change as it goes from air to glass. And that's what we will put. Where's my pen? If you wanted to put about the bending of light too, you can, because it actually involves the bending too. But the reason why we choose speed is because it is the change in speed that is causing it to be bent. So that's why when we're defining it, we just talk about the speed of light. I'm going to finish writing. So the fact is a ratio which tells how much the speed of light changes as light travels from air to glass. Okay. Now, would you like to put any, or do you think of any other information that you could possibly put to ensure that you get your full 3 marks? Okay, awesome. See with me. I don't know if PXL I don't know how to pronounce it. PXL is pronounced a specific way, but good job. Congrats on passing CSEC physics. Excellent. And yes, CSEC, we could put the formula. Excellent. So we could say it is calculated using the formula N equal sine I, or you could put theta 1 over sine R. And you can put sine I is air, sine R is glass. So that is definitely ensuring that you get your full 3 marks. All right. So we're moving down. Figure 7 shows a ray of red light incident on the face XY of a glass prism at point S. Please pay attention to this part, I beg you. The path of the ray is shown in the diagram. The refractive index N of the glass for red light is 1.5. So, let's analyze what they said to us. They said this figure that they have, it is showing a red light that is incident on this face here. There, this is XY. X, Y. So it's this face. And we can see it here being an angle of incidence. And here is point S. It says at point S. The path of the ray is shown in the diagram. The refractive index N of the glass of red light is 1.5. It says calculate the angle of refraction in the glass at S. Now we just put the formula here, and this is the formula that we'll be using to help us. But let me zoom in a little bit. There is something here that you need to take note of. In order to find the angle of refraction, we will naturally need N, and we know that N is 1.5. They gave us that. We will need I, the angle of incidence, and we need to calculate R, the angle of refraction. What is the angle of incidence? What is the angle of incidence? Look at the diagram, tell me the angle of incidence. So we're working at point S. All right, I'm seeing your response, Janelle. Casey, what do you think? All right. So we're going to explore, while I'm waiting to see if Casey is still here. We're going to explore now. Our Casey says same. Okay, awesome. So we're going to explore now what the angle of incidence is, or how angles of incidence or refraction or reflection, how are those angles measured? They are measured between what and what? The angle, for you to get the angle of incidence or the angle of refraction, or if we were doing reflection, the angle of reflection, you have to measure that angle between two specific points. What are those two specific points? Let me get my red ink in the meantime. Let me make it a little bigger. Yeah. Ah, yes, Casey. Has to be the normal. So it must be measured between the ray, and this is our ray here. Has to be measured between the ray and the normal. So your angle of incidence would actually be right here. So this 55 is a trick. So now that we've clarified that, what then is the true angle of incidence? It would be 90 minus 55, which is equal to 35. So that is our angle of incidence. Have to look out for these things. They oftentimes do this to try and trick you, but you're not going to be tricked because you are going to remember where the angle of incidence or the angle of refraction or reflection, you are going to remember where it is measured. It is always, no matter if it's incident or reflection or refraction, it is always measured. Do this again. It is always measured between the angle of the incident ray or whichever ray and the normal. So it's 35. So now we can go and write our equation. So we have n equals sine 1 or sine I divided by sine r. We want to find, yes, Janelle, I'm happy you're here so that you can make those final tweaks in your preparation. No problem. So we want to get the angle of refraction because that's what they asked us for. So we are going to transpose this equation now to get sine r as the subject. So I'm going to multiply both sides by sine r, being that it is being divided on that side. So that will cancel that. I'm going to draw a line here to go to the next side. So n times sine r is equal to sine I. So we want to get this, so we divide both sides by n now. So we get sine r rather, is equal to, and I'm just going to substitute the sine of 35 divided by 1.5. Do that one for me and let me know what your answer is. All right, good. Good evening, Rashid. Yes, it is 0.38. So remember, this is sine r. They ask you for the angle of refraction, so it really and truly should not be a decimal. So if you see the decimal, you know that you're not done yet. So we know that therefore r is going to be equal to the inverse of sine times 0.38. It's going to be equal to that. Someone do that for me and let me know what you get. Sine inverse 0.38. Wait, we didn't divide by 1.5. We left out that. Let's go before we reach there. So let me erase this part. 0.38 divided by 1.5 gives us what? Okay, y divided by 1.5, not sine 1.5. Okay, so this is what we should have on this side. So based on the equation up here, it's sine of 35. We didn't do sine of 1.5. Because remember, the original formula is n is equal to sine of I the sine of I divided by the sine of R. So at no point did we put sine for the refractive index. And remember, the 1.5 is the refractive index. So when we transpose, we get sine R is equal to sine I divided by n. When we did sine I, that's sine of 35, we got 0.38. We now need to divide that by 1.5. So we divide 0.38 by 1.5. What do we get? I saw the answer not too long ago, but I'm not seeing it anymore. The answer was there. Right. Sine of 35 divided by 1.5. Is that? Let me check. Hold on. What am I getting on my calculator? Oh. Okay. Never mind. Right. It is 0.38. So here we go. Made a little error here. So let's cross this out. I'm using a calculator now. So this is equal to 0.38, the full thing. So sine 35 divided by 1.5 is awesome. So now we need to find sine inverse, got ahead of myself there, times 0.38. And what do you get for that answer? Thanks, Casey. So when you find sine inverse of 0.38, what did you get? 22. Excellent. I know I saw 22 at one point. So that's your answer for the angle of refraction. Any questions before we move on to the next question? All right, not seeing any. So we move full speed ahead. All right, Casey says no, good. Okay, so the next question now asks us to calculate the critical angle C for glass in air. Critical angle. And I'm not going to preempt one of the questions. I was going to ask a question, but that's going to preempt the question. So I'm not going to ask it. I'm going to wait until we get there. So the formula to find critical angle, or the formula that relates to critical angle, let me say it like that, is sine C is equal to 1 divided by n. And notice they put here critical angle, comma C. That means the symbol for critical angle is C, which you would have known already. So we have 1 divided by, and we know what n is already, 1 divided by 1.5. That gives you what? Janelle? 1 divided by 1.5, you still there? Okay. Round it off, Janelle, you have 0.6. You'd have seen 0.66 going down. So round it to 2 decimal places. Oh, good job. And good job, Casey. So that's 0.67. That is sine C. So therefore, C is equal to sine inverse 0.67. What's that answer? 42. Beautiful. So the critical angle is 42 degrees. Final one for question 4. Identify the critical angle C in figure 7 on page 14. That one now I'm not going to go there first. I want you to tell me, what is the critical angle? By definition, what is critical angle? And by knowing the definition, that's how we'll be able to find it on the diagram. Because we have to know what it is. Okay, good, Rashid. What is the definition or the definition for critical angle? What is critical angle? While I'm waiting, I'm just putting in the other questions to make us move smoothly. Anybody knows what critical angle is? If by the time I'm done pasting this final question in question 5, if I don't see an answer, then I'll tell you. I know you're probably typing, so it's taking a little longer. All right, so I'm not seeing the answer yet, so I'm going to tell you. I'm going to write the definition here. No, they didn't ask you to define it. They just want you to find where it is on the diagram. But I'm going to write the definition so that you are able to follow. So the critical angle is an angle of incidence, and I'm going to underline that part, that produces, an angle of refraction of 90 degrees. So that's the definition. The critical angle is an angle of incidence. It is an angle of incidence. What is special about this angle of incidence is that, let me use a different color now, it's going to produce an angle of refraction of 90 degrees. But the critical angle is an angle of incidence. Let's go over now to see if we can identify. So it's easy to identify this one because you can work from the back end. So you can look if you see an angle of refraction of 90 degrees. And then what you do after you find that one is to look which angle of incidence produced it. So you're looking for an angle of refraction of 90 degrees. Tell me the face along which that angle of refraction is. angle of refraction of 90 degrees. Which face is that angle on? All right, so I'm seeing Z. So I'm assuming you mean YZ. Good. Good job. Good job, Janelle. And that is the face. So if you look along this face, you are seeing, I remember the angle is measured between the ray and the normal. So you are seeing that the angle here is running along this face, and you know your normal is perpendicular or 90 degrees to the face. So this angle here would be our 90-degree angle. So that means that is the angle of refraction that was produced. That is the 90 degrees angle of refraction. So now remember we said the critical angle is the angle of incidence that produces this angle of refraction that gives 90 degrees. So that simply means if this is an angle of refraction, then the angle of incidence must be here. This is C. But I want you to remember, the critical angle rather, is an angle of incidence. The 90-degree angle that is produced is not the critical angle. That is a normal angle of refraction. Critical angle is an angle of incidence that produces an angle of refraction of 90 degrees. So Janelle asked, why not on the outside? You mean like right here? Use a different color to ask where you're talking. Let's use green. You mean like here? Which outside are you talking? Where I have the green? No, over the dotted line. The dotted line is your normal. So I'm going to use a different color. Oh, let me use highlighter. You're talking about this. Okay, the yellow not showing so well. Let's use a different color highlighter. Blue. Highlighter needs to be a little bigger. Almost, where are you? You mean this dotted line, right? Or were you talking about this angle? Let me use a different color. They can tell me which angle you're talking. Let's use pink. Or blue. Which color are you talking? The highlighter, blue or pink? The angle on top of the blue. Oh, so you're talking this angle out here. Let me erase the others. So you're talking this angle here that I have left. Okay. Now at this point, there is no ray. There's no incident ray there. And remember, the critical angle is an angle of incidence. What you have here is just the side of the prism and the normal. For you to get an angle of incidence or an angle of refraction, it has to be an angle between the ray, like in this example, and the normal. So the angle for this angle of refraction is between the normal here and the ray here. So the rays are usually shown to with an arrow. So you can pick up that it's a ray. So that's a ray of light. It's indicating how light is traveling through, in this case, the prism. Right. So that's why our angle has to be between the ray and the normal. Another way that you could know, let me erase that a little bit. Another way you could know is if we are working with an angle of incidence and we're talking about it producing an angle of refraction, it therefore means that the light has to be passing from one medium to another. That's what it simply means. It has to be connected or be coming from one medium to another. So here you have it's coming from glass and would be exiting into air. Out here would be air. But because it's a critical angle, it didn't quite go out into the air. It went along the edge of the prism. But once you're dealing with refraction, there has to be one medium as the incident and another as the refraction or the refracted medium. So that's why. Hope that clears it up for you. But remember, your angle is measured between a ray and the normal. Okay, you're welcome. All right, so that wraps up question 4 rather. And we got our 3 marks because we have our unit and our answer, that's 1. We substituted and we have our formula good. We drew, we identified where critical angle was. So that's 3, that's 1. And we defined up here, that's 3. We mentioned glass in our definition. So that's definite. And here we got 3 because we had our unit, formula, and we substituted. Excellent, we got our full marks. So now we move on to question 5. Define the term electric field. Now realize when they gave us this question, they did not make it specific to anything. So when we're defining in this scenario, we can just say what electric field is. We don't have to say electric field and putting anything specific like we had to do a while ago with the refractive index. Right? So that's what I'm talking about when I say to you, if you see them mention something specific for your definition, you must include that in your definition. So electric field, what is that? So an electric field is the region, change my ink color. The region around a charged object in which another charged object will experience a force. And we know our primary school definition, a force is a push or a pull. So it will experience a push or a pull, will experience a force. So the electric field is a region around a charged object in which another charged object will experience a force. Next part, figure 8 shows a positively charged sphere which is attached to an insulated stand. Draw arrows to indicate the pattern and direction of the electric field in the region surrounding the sphere. So we're dealing with a sphere, meaning, round objects. Our field will take the pattern like this. Now, we determine the direction of the field. And I usually just tell my kids to, just imagine, if you can't remember, just draw a little positive charge. And it is, the field is determined, the direction of the field is determined by the direction a positive point charge would go if it's placed in that area. Now we know the principle. Like charges do what? What do like charges do? Like charges repel. Good. Like charges repel. And opposite charges. All right, Janelle, so you just got that one. So like charges, positive and positive, if you bring them together, they are going to repel each other, push apart. And what if it was a positive and a negative that you brought together? They will attract. Excellent, Casey. Excellent, Janelle. Awesome. So once they are opposite, they are going to attract each other. But if you bring positive to positive, they are going to push apart, so they repel. If you bring negative and negative, they will repel as well. So back to this little thing now. So if we're saying that the direction is determined by the direction a positive point charge would take if you place it in the field. So help me out. If I was to take this little, I can move it, yes. If I'm to take this and bring it into this field, because these are my field lines, indicating that there's a field around the sphere. If I put my positive charge here, so what is it going to do? Which direction is it going to move? It's going to move towards the sphere or away from the sphere? Is it going to move towards or away? Bringing my positive point charge in this field. Is it going to go? Awesome. It's going to go away because they are like charges and like charges repel. So that simply means my field direction now is like this. So remember, the direction of the field is determined by the direction a positive point charge, and positive point charge just means it has a single charge on it. That's all it means. So you're just thinking, if I put this positive charge in this field, which direction are you going to go? You're going to go away from it. So that is the direction of your field. Good? That would have been our 2 marks, because the question says, draw arrows to indicate the pattern and direction of the electric field in the region surrounding the sphere. So indicate the pattern. The pattern is drawing the lines like that. So if you only drew the lines, you'd have gotten 1. But then when you put on your arrows, you get your second point. So that is 2 marks. And we just got it. So now we move on to the next question. So this one says, a smaller uncharged metal sphere Q. Here's Q. Q now is brought, it's suspended first by a cotton thread and brought close to the positively charged sphere as shown in figure 9. Draw the distribution of charge on sphere Q. Now let me ask you, what is going to happen inside Q when you bring it? It's uncharged, so it's neither, it doesn't have excess of positive or negative. The positive and negatives in it are balanced. And that's what we mean when we say something has no charge. For something to have no charge, it means the number of protons and the number of electrons within it are equal. It doesn't mean it has no charges. It just means that the number is equal. So Q has equal number of electrons, equal number of protons. When we bring it close to this metal sphere, what will happen? Negative will move to the left, positive will repel. Excellent, Rashid. Excellent. So anybody knows what that concept is called? When you bring an uncharged body close to a charged body and it causes that moving apart. Anybody know what that is called? Yes, KCL, yes it is. Negative charges will go to one side of the sphere. All right, good job. Anybody knows the name of that concept? Induction. You are in the right area, but you didn't quite hit the nail on the head. When you have positive moving to one side, negative moving to one side, what are they doing? If positive moving one side and negative moving one side, what are they doing? It's an S word. S word, what are they doing? Positive say, hey, I'm going over here. Negative say, hey, I'm going over here. What are they doing? S word. Let me see how much letters. 8 letters. Let's go for our spelling challenge again. Ends with an E. And has 3 other vowels. Some of them may be repeat vowels. Second letter is E. I feel like I don't spell this word right. No, it's spelled right. Positive moving one side, negative moving one side. What are they doing? This letter is T. You must get it now. No. Last letter I'm giving you. Ah, good job, Rashid. Yes. If positive moving to one side and negative moving to another, they are separating. The concept is called charge. And I'm going to change this part. Separation. See how easy? It's like they just didn't bother to make life hard at this point. You just say, all right, since they separate, we just call it charge separation. So that's what it's called, charge separation. All right. So let's say we're to draw the distribution of charge on sphere Q. So Rashid told us that negative will move to the left. And that's because they are attracted. Let me use a different color. Because they are attracted to the positive. So they move a little closer. And positive, and because they're balanced, I'm going to put the same number of positives here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So when you are doing it, ensure that you put the same number of charges on both sides as well. I'm going to show you a simulation. Not sure if you are familiar with it. That shows exactly what is happening in terms of this charge separation business. Really cool stuff. It's what happens in real life, but we're not quite able to see. Let me see. Where are you? Here we go. So I'm going to stop sharing for a little bit. And then stop screen. And then I'm going to go and share that screen. So I'm going to show you how this charge separation thing occurs. Waiting on the tab to be fully loaded, or it's loaded. Balloons and static electricity. Not sure if you're familiar with static electricity. I mean, not static effect simulations, but this is the one I'm using. And it basically is a very good platform that I can use to demonstrate certain concepts that we're not able to see or we're not able to do in a lot of situations sometimes. So you notice this sweater has a whole lot of positives and a whole lot of negatives. This wall has a whole lot of positive and a whole lot of negatives. This balloon only have 4 each, but all 3 objects are neutral. They are they have 0 charge, meaning they have 0 excess. So none has more positive than the other. So we'd say that it has no charge. All right. So what I'm going to do now, if you're familiar with static electricity, I'm going to charge the balloon by rubbing. That's a method of charging. And when we talk about charging objects, what we are saying is we are causing it to have excess of one type of charge. That's what we're doing with charging things. We're letting it have an excess of one type of charge. So I'm going to take my balloon here. Yeah, look at that. What charge does the sweater now have? Good. The sweater is now positively charged. What charge does the balloon now have? Good, Kesia. Good, Rashid. The balloon is now what charge? So sweater is positive. Balloon is negative. Good. Has excess negative, so it is negatively charged. Now pay keen attention to the wall. I'm going to bring the balloon close to the wall. Look what is going to happen inside the wall. Seeing that? As I bring the balloon close to the wall, what is happening to the charges inside the wall? All right, so I hope you are seeing what I'm seeing. The balloon is negatively charged, and when you bring it to the wall was neutral. The negatives in the wall repelled, and so they pushed apart. They pushed far to the far side of the wall away from the balloon and leaving our positives there. So notice the positives didn't move. It's just the negatives that moved to the far side, showing repulsion. Right. So the negatively charged balloon attracted the positive and it repelled the negative. That is what is happening. So when we look at, let me go back to the question we were doing. When we look at the question we were doing, we are going to see why this happens. So that's why when you bring this uncharged sphere close to the charged sphere, the negatives will align close to that side. That's the side that is closer to the sphere. And the positives are going to be more to the back. All right? So that's what's happening. Charge separation. Good. So they said draw the distribution of charge on sphere Q. We would have gotten our 2 marks because 1, we draw both positive and negative on it. And number 2, we show the charge separation where negative is close to the positive and positive is on the side further away. So that is charge separation, and that's what's happening. So we just got our 2 marks. Moving along. An earth wire was briefly brought into contact with the sphere, as shown in figure 10. Then it was removed. Describe what happens in the wire and state the final charge on Q. So I'm going to put a diagram to show you what's happening. So we had 5, 1, 2, 3, 4, 5. Then we had 1, 2, 3, 4, 5. Then I'm going to change color to blue. Then once this earth wire now is connected, you're going to have negatives going up the wire from earth. And what those negatives are going to do is to come over here and balance out this side of the sphere, making this side now neutral. So it's balancing the excess positive charges. Where's my mouse? It's balancing the excess positive charges that were here by allowing negative charges from earth to flow to that side. So now this side is neutral. Now when it is removed, those negative charges that this sphere got are going to remain. So when it remains, remember this side was neutral, because we had 5 positive here and we get 5 electrons to balance it off. So when you remove the wire, what will be the charge now on Q? Net charge of Q will be what? Negative. Very good. It's going to be negative because when those charges, those negatives came and neutralized the positive, remember that you still had negatives over on this side. So when you remove the wire, you are now going to have excess electrons, and so the charge will be negative. Very good, Casey. So let's write that. So it says describe what happens in the wire and state the final charge. So what happens is the wire, where's my mouse? Oh, it changes to black. Electrons flowed from earth to the positively charged portion of the sphere, portion of Q, causing that side to have a neutral charge. When the wire is removed, so we could say it flows from earth, we could say through the wire, just to make sure that they know it's going through the wire. Through the wire to the positively charged portion of Q, causing that side to have a neutral charge. When the wire is removed, Q will have a net negative charge. And that's your answer for 2 marks. Now, what the Earth is described as having, it's like a sea of electrons. So what it does, it takes electrons where there are excess or gives electrons where there is a deficiency. So let me give you another scenario, not in the question, but hey, we can apply our knowledge across. Let me put you a little way away. So what if we had a sphere that was negative? We brought, let's not name this Q so we don't get confused. Let's name this P, and it is grounded. What would, let me go to charge separation, because we know what's going to happen in charge separation. So we have charge separation when you bring it close. What happens when you bring the wire? Will electrons go to the sphere or leave the sphere? Go to P. Will electrons go to P or leave P? Very good. It will leave P because this side of the sphere that the wire is connected to has an excess of electrons. So these electrons now, they are going to go down this time. So they're going to go down to Earth because they're going to be seen as excess. So they're going to go down to Earth. When you remove the wire now, what charge will P have? Okay, Janelle said go again. Let's go again. How far should I go from? Let's go from, let me take out those electrons that I just let leave. So I'm just doing the opposite scenario to what we have there. You have positives and negatives. So that is because we brought it close to a negatively charged sphere. Right? So when you bring P now close to it, just like what happened with Q, you're going to have charge separation. Positives on one side, negatives on another. Now, when you connect the earth wire to it, because this side has excess electrons, these excess electrons will now flow down to Earth. Remember I said the Earth is like a sea of electrons. It collects electrons where there is an excess or gives electrons where there is a deficiency. So these excess electrons on this side are going to flow down to Earth. When the wire is removed, P will now be positive. So let me draw P another time. So P will know when the wire is gone, P will now be positive because it will have an excess of positive since those electrons that would neutralize it flow down to Earth. Okay, great. She says, okay, awesome. So even though that wasn't a part of the question, I just did it so that you could get a good understanding of that concept. And we're almost done. Question 5. The battery in an electric car can be charged by passing a current of 11 amperes through it. Calculate the charge stored in the battery after 8 hours. So let's record what we got. We know that the quantity that has unit ampere is current. So we say I is equal to 11 amperes. Then we know that we got time. It says 8 hours though. But when we're dealing with time, we normally work with seconds. So I have to convert it to seconds. To go from hours to second, let me carry you through the chain command. We have to multiply by 60 to get how many minutes. Then we multiply by 60 again to get how many seconds. So 80 times 60 times 60 is 80 times 60 times 60. What did you get? I got an answer. Testing if we're going to get the same answer. 28,800. That's what I got too. Seconds. Awesome. So now what's the equation that we need to use? They asked a charge. They gave us current and time. What's the formula? Awesome, Janelle. Got the same one. What's the formula here? Q equals IT. Excellent. So Q is equal to IT. So that is 11 amperes times 28,800 seconds. And when I did that, I got 316,800. Did you get that answer? Okay, excellent. So that would be your answer. And remember that the unit of charge is coulombs. Symbol capital C. Last part, this is what I was saying to you, that this question only has a bit of current calculation, nothing extreme. But tomorrow we will look at those. So we have calculate the resistance of the battery. We have voltage here. They gave us voltage. We have current, we have time, we have charge. Which equation will you use to get the resistance? While you tell me that, let me just get the questions for question 6 so that we can wrap this up and be done with it for this evening. Which formula will you use to calculate the resistance? V over I. Excellent. So the formula is coming from V equals IR. I say VIR. So you have VIR and you have quit. I call Q equals IT quit. Not telling anybody to quit learning physics. Never. Physics is an awesome subject. Okay, so here we go. So just to show where we're coming from V equals IR. And we transpose because they want resistance. That would be divide both sides by current. So R is equal to voltage divided by current. Very good. So let me just put that one up. Yep. So that's the equation that we're working with. So the voltage we got is in 220 volts. And the current we got was 11 amperes. So with that, 220 divided by 11 gives you 20 ohms. Excellent. I like how I got my unit a while ago. Yes. We getting it. Excellent. I like how I'm seeing my units. Yes, Casey, I'm seeing your units too. I like how I'm getting my units. Awesome. So it's no longer just 20, but it's 20 ohms. Awesome stuff. And once you would have done that, you would have gotten your full 3 marks because you did formula, you substituted the values in, and you got your answer with your units. Almost done. That wraps up question 5. So notice this one is 4 marks. They're going to give you 1 mark to convert the time to seconds, and then 1 for your formula, 1 for substitution, 1 for the answer with the unit. And that would wrap up your 4 marks. So you see, we're maxing out our paper, getting full marks on our paper. Over to the final question. Yay! Question 6. So question 6 says complete table 2 by inserting the type of radioactive emissions and their properties. So you see this table now and you say, Lord, is which one this? Look at how you're going to figure it out. The nature is filled in for all of them. And if you remember anything about radioactive emissions, you know that once you see electron, that is beta. And if electromagnetic radiation, you're not so sure what is going on for that. You see the next one says helium nucleus, you know that is alpha. So the third one must be gamma. Yes, Casey, you're awesome. Must be gamma. So, okay, trying to remember what is going on for the other side of the table now, all right? What is gamma stopped by? If you just write down lead, you get your mark. Because remember that is the most dangerous one, is high energy. So nothing really, or it's not every anything can stop gamma. So you say, oh, lead. Alpha now. Alpha is I'm just going to tell you this one because you're going to need to know this one. But gamma you will know because gamma is lead. And it's stopped by 1 sheet of paper. So its range in here is about 1 to 3 centimeters. Not very far. Beta now, we know beta is more penetrating than alpha, so that's why it went a few meters. It stopped now by a few millimeters of aluminum. You can put that. Once you do that, you get your 3 marks. How I think these 3 marks will be distributed, once you get everything across the line correct, then you get your 3 marks. Could be that. Or I could say every 2 you get wrong, you lose a mark. Could be that as well. But we got our 3 marks because we did everything in the table. Awesome, Casey was there with me. And concrete too, yes. So let it stop by a few centimeters of concrete. But if you're, the one thing you're sure of, it is stopped by lead. Cannot go any harder than that. Isotopes. What are isotopes? This is one of my favorite topics. I like this. I like electricity. Actually, I like all the topics, but I have a special love for radioactivity. I do not know why, but I absolutely love radioactivity. So define the term isotopes. They are atoms of the same element and this is only one way of defining it. I'm going to tell you another way you could have defined it. Just a little tweak. Having the same number. Same number of what? Same atomic number, different mass number. Excellent. Excelente. Same number of protons, but different number of neutrons. There you did. You get your 3 marks. So it's atoms of the same element having the same number of protons but different number of neutrons. If you didn't want to put the part about element, which it's very critical, but if you wanted to say they are atoms which have the same number of protons but different number of neutrons, that could go as well. When we say atoms of the same element, what we mean is each element, you can identify elements by their atomic or proton number. That's what defines elements, the atomic number. So once you are having more than one atoms having that same proton number, doesn't matter if the neutrons are the same, as long as the protons are the same, then they are isotopes. And they would be the same element. And if you wanted to give an example to make sure you get your 3 marks, like I said, they're really going to give me 3 marks for this, you just give them an example. And you put carbon. What is the atomic number for carbon? Atomic. The 12 is correct, but it's correct for something else. Right, carbon 12 and carbon 14. When we are talking about isotopes, we usually refer to them by their mass numbers because as we know, the proton number is the same. So carbon 12, carbon 14, the 12 and the 14 are proton numbers. Good. The atomic number for carbon is 6. If you did carbon 12, carbon 14, you would have still gotten it correct. Because like I say, we normally refer to isotopes when we call the numbers, it's mass number. So you could either say carbon, write it like this, or you put carbon 12, carbon 14. Anyone works. Now we see another one here. The structure of the atom of an element Y, showing the number of neutrons N, protons P, and electrons E, is represented in figure 11. State the mass number and atomic number of this atom. We know that mass number is equal to, what is mass number by definition? Or by formula? Mass number. By definition, what would we say is mass number? Excellent. Protons plus neutrons. So we look here, 5p plus 6n gives you 11. And atomic number is the number of protons. What is the atomic number? Excellent, Rashid. You're on a roll. Good job. So let me just say, guys, remind you, once we're dealing with radioactivity, we are dealing with the nucleus. So yes, we know that the atom has electrons in it. We're pretty aware of that. But radioactive emissions come from the nucleus. So we're only working with the number of protons and neutrons. Somebody might say, but Miss, how electrons occur then? Not electrons, beta. How does beta fit into this? Beta, that emission is also from the nucleus. Remember, for beta, you have a neutron splitting into proton and electron, and the proton goes into your nucleus, the electron is emitted. So once we're dealing with radioactivity, We are dealing with the nucleus of the atom. That's why even in the equations, you don't see anything about electrons. It is how much protons, how much neutrons, and we know those are in the nucleus. So for this question here, we gave the proper definition, and just to make sure that they give us 3, we gave them some examples, so we definitely get our 3 there. And for here, we definitely get our 2, because, hey, we told you the mass number and the number of protons, so we're good. Final page coming up. Write the symbol for another possible isotope of element Y. Another possible isotope rather for element Y. So first we can start with is Y. So I want you to write not just the mass number. I mean, you can. If you do that, they can't mark you wrong because it's correct. But I want proton and neutron just to make sure that we are understanding what we're going about. So tell me the proton number or atomic number for this other element or this isotope of element Y. Tell me the proton number. Proton number. What's the proton number? What's the proton number for this isotope of element Y? Oh, okay, so I went even a step further. She didn't just give me proton number, she gave me neutrons too. Okay? So she said 5 protons, 12 neutrons. So she could also write it to be Y17. Good job. We could also have Y, that was what, Y11. This could be Y12. Or it could be Y13. So let me put 13. 13 is 6 here. And no, not 6, 5. 5 here. And 5 plus what? 13. 8 up here. So that would give you Y13. Y12, you would have 5 here. 5 plus 7, 12. There you go. So you could have written any number that you so choose. Very good, Casey. So now to do some equations. Yay. All right. So polonium-210 nucleus decays, one of them. This is a sample they're giving us. A polonium-210 nucleus decays by alpha particle emission to a lead nucleus. Complete the equation for the decay of polonium-210. So we are writing our equation. So we have, they gave us a symbol for lead. So we know that polonium is going to lead plus alpha. So let me write my alpha symbol. Now we know what is the atomic and mass number for alpha. Okay, beautiful. Not for N case here, it would be the mass number that's 4. So the N there would be representing the number of neutrons. So it would be mass number is 4, but proton number is 2. So in this case, the number of neutrons would actually be 2. So remember, mass number equals proton plus neutron. And that's why up here I would have had 17 because the proton number is 5, the neutron is 12. So when you add them, you get 17. So for alpha, it has 2 protons, and being that its mass number is 4, it must have 2 neutrons as well. All right. So yes, and we add our energy over here. So for alpha, we know that the mass number is 2. Not mass number, atomic number is 2, mass number is 4. So now we need to work out, then why do I feel I wrote it too close? I think so. Let me go again. I wrote lead a little bit too close. Oh, I started writing in red, didn't even realize. So atomic number 2, mass number 4. So now we need to add the values here, and they should be equal to the values over here. So we already have proton number as 80 as 2. 2 plus what give you 84? Or you can simply say 84 minus 2. Any way you want to do it. What's my proton number for lead? 82. Excellent. And 210 minus 4. Or we ask what plus 4 gives you 210? 210 minus 4. 206. Excellent. So let's do a check to make sure that our right side is balancing with our left side. 206 plus 4 is 210. Excellent. 82 plus 2 is 84. Very good. So our answer done. We get our 3 marks. We have our symbol, we have our product, and we have our alpha there. Done. Just got our full marks for that question. And ding, 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 ding. Final question. So it says polonium-210 has a half-life of 138 days. At a certain time, a sample contains 6.4 times 10 to the 6 polonium nuclei. Calculate the number of polonium nuclei remaining after 522 days. First thing we're going to do, we can approach this in many ways. Let's take this approach. Let's find out how many half-lives there are over these 552 days. So we say, okay, number of half-lives equals 552 divided by 138. How many did you get when you do that? When you divide 552 by 138, what's your answer? 4. Excellent. So that means it takes 4 half-lives to get to 552 days, okay? So now you can use any method you want to decipher how many are left. Remember the question asked you for the number of polonium nuclei that remain. It didn't ask you for the number of half-life. So you can't do this as you finish, right? Now I'm going to do the arrow method to determine what remains. Now remember, half-life is the time taken for a sample to reduce to half. So the sample in this case is 6.4 time, or should I put it down here? I think I have more space down here because I have to go through 4 half-lives. I'm still using red ink. I did not even realize. I'm going back to black. So 6.4 times 10 to the 6 after 1 half-life, the arrow representing half-life, what will remain? Simply do that value divided by 2. What do you get? Because remember, half-life is the time it takes for it to reduce to half. So when you go through 1 half-life, which is 138 days, after that 1 half-life, how much of the sample are you expecting to see? You don't have to tell me well, no, let me actually let you tell me the full thing. Tell me the full answer. How much is left? Any quick fingers? No quick fingers? All right, so I'm going to tell you the answer. I'm almost sure by the time I start writing, I'm going to get the answer. Going to another half-life. Actually, that's another 138 days. All right, I'm going to give you the answer. 1.6 times 10 to the 6. Another half-life. Remember, we are going for 4 half-lives. So that's 1, 2, 3 half-life. 1.6 divided by 2 gives you 0.8 times 10 to the 6. Awesome, awesome. SK, so you're catching up. Another half-life, which is our final half-life. 1, 2, 3, 4. So after the 4th half-life, we have 0.4 times 10 to the 6. But as physicists, we know we cannot write, excellent case here. We cannot write a number in standard form with 0 point. So, simple. If you want to write it in full first and then write it back in standard form, you can. So let me just do it that way as an easy way for you to convert. So that times 10 to the 6 is equal to 0.4. And I'm going to move my decimal place 6 times to the right because the power is positive. So it's 1, 2, 3, 4, 5, 6. So that is equal to 400,000 or 4.0 times 10 to the 5th. And with that, we got our 3 marks, which means we got everything right on the paper. Yay, we're done. Awesome. So we did all 3 questions. Awesome, 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 awesome. And that means we are done, 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 done. Dun, 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 dun. End of exam. We would have gone through the topics. Let me go from beginning. The first question was simple pendulum. We would have gone through simple pendulum. Then we went through pressure. Then we went through heat. Then we went through waves. Then we went to, and to be precise, we went through diffraction and refraction. And then we went through electricity. And then, and then, move my screen. Not moving. Okay. And then we went through, yeah, we did some calculations. Then we went through to radioactivity and we are done. Congratulations to everyone who is on. Let me send you some love. Congrats to you all. We did it. We completed the 2023 January paper. You were an excellent, 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 excellent audience. You worked along with me, and I hope that you are feeling even an inch more confident going into your exam on Monday, knowing that, hey, I thought I wasn't good, but actually turned out to say I actually know to answer questions. Yay! So join me tomorrow. I think tomorrow is going to be about 7 o'clock. So join me tomorrow when we are going to work some questions on electricity and magnetism as you requested. So I'm not going to just find a one paper. We're going to work questions on electricity and magnetism. So guys, join me then. Until then, see you and have a good night. Make sure you get rest. Remember, my motto is always get rest. Even though you're studying, make sure you get rest. So get some rest so that your brain can fire. All right, guys. So see you in the next one. And thank you all for coming. Bye. Oh, this live stream will end in 5, 4, 3, 2, 1 3/4, 1.5, 1 1/4. Bye.